Welcome to our channel. Today, we're diving into some groundbreaking findings from the James Webb Space Telescope. We're unraveling the mystery of early galaxies that, it turns out, weren't as massive as we once thought. Join us as we explore this fascinating update in our understanding of the universe's infancy. A new study suggests that black holes might be the hidden force that shaped the early universe, causing it to host far more massive galaxies than previously thought. This revelation comes courtesy of NASA's James Webb Space Telescope, JWST, the most advanced space observatory ever built. Launched in December 2021 with a budget of $10 billion, JWST excels in capturing infrared light similar to how night vision goggles work. Researchers are utilizing the JWST to peer back into the nascent stages of the cosmos. Since the universe's inception from the Big Bang, roughly 13.8 billion years ago, it has undergone significant expansion. This expansion stretches the light from distant galaxies, causing them to appear redder by the time their light reaches us, akin to how an ambulance siren drops in pitch as it speeds away. The JWST's sophisticated design enables it to detect this stretched, infrared light from the universe's earliest galaxies, providing a unique glimpse into our cosmic beginnings. When astronomers peered into the depths of the early universe through the lens of the James Webb Space Telescope, JWST, they anticipated discovering galaxies that were smaller, simpler versions of those we see today. Instead, they were stunned to find some galaxies that had grown astonishingly large in a surprisingly short time. This discovery challenged the prevailing notions of cosmology, the science of understanding the universe's composition and its evolution since the Big Bang. According to study co-author Steve Finkelstein, an astrophysicist at the University of Texas at Austin, these early galaxies were about twice as large as what the standard model had predicted. This revelation, shared with Space.com, suggested a significant recalibration of our cosmic understanding might be necessary. However, a twist in the tale emerged in recent findings published on August 26 in the Astrophysical Journal. Finkelstein and his team found that some of these seemingly colossal early galaxies were actually much less massive than initially believed, adding another layer of complexity to our understanding of the universe's youthful epochs. In a groundbreaking study, researchers analyzed 261 galaxies formed between 700 million and 1.5 billion years after the Big Bang. Traditionally, to gauge a galaxy's mass, scientists measure its light output and infer the likely number of stars generating that luminosity. In the past, using NASA's Hubble Space Telescope, only the brightest, most massive stars were visible. However, the James Webb Space Telescope, JWST, captures redder wavelengths, revealing the presence of cooler, lower-mass stars, thus providing a more complete picture of a galaxy's stellar population. The team uncovered that the luminosity of 9 of these early galaxies was amplified by black holes at their centers, causing these galaxies to appear brighter and therefore more massive than they actually are. Black holes, known for their intense gravitational pull that prevents even light from escaping, can cause incoming gas to emit bright light due to the heat generated from its high-speed frictional entry into the black hole. When these black hole-affected galaxies were taken into account, the discrepancies with the standard model of cosmology were resolved. So the bottom line is, there is no crisis in terms of the standard model of cosmology, Finkelstein stated in a press release. Anytime you have a theory that's been around for so long, you need overwhelming evidence to discard it. And that's simply not the case here. Furthermore, the study's lead author, Katherine Chorowski, a graduate student at the University of Texas at Austin, noted in the press release, "While we are still finding more galaxies than predicted, none of them are so massive that they break the universe." This insight reaffirms the resilience of established cosmological theories, while highlighting the enhanced observational capabilities of the JWST. One intriguing hypothesis for why the James Webb Space Telescope, JWST, observes about twice as many massive early galaxies as the standard model predicts is that star formation in the early universe may have been more rapid than it is today. Perhaps early galaxies were more efficient at converting gas into stars, suggested Catherine Churowski in a press release. The birth of a star begins with a gas cloud collapsing under its own gravity. As the gas contracts, it heats up due to friction, creating outward pressure. In the modern universe, these opposing forces typically slow down the process of star formation. However, the denser conditions of the early universe may have made it difficult to expel gas during star formation, allowing stars to form more quickly. We're eager to delve deeper into why we see what we see, explained Steve Finkelstein. A key approach is to investigate how these galaxies accumulated their stellar mass. Upcoming data expected in the next few months should shed light on this process, enhancing our understanding of how these colossal early galaxies came into existence. The James Webb Space Telescope, JWST, has given astronomers a new window into the cosmos. Recently, it turned its powerful lenses toward the early universe, and what it found has subtly shifted our understanding. Initial theories posited that the first galaxies were colossal massive beyond anything existing today. However, the latest data suggests a different narrative. These early galaxies were actually smaller and more numerous than previously believed. Why does the size of these ancient galaxies matter? The mass and structure of early galaxies influence everything from star formation rates to the eventual evolution of galaxies they would become. Smaller galaxies in the early universe suggest that the process of galaxy formation was more gradual and involved numerous smaller building blocks rather than a few massive ones. This finding impacts not only our understanding of galaxy formation, but also the broader theories about the universe's overall timeline. The JWST's observations utilized advanced infrared technology to peer back over 13.5 billion years, to a time when these galaxies were just forming. What's remarkable is how these observations challenge the robustness of our current models. The technology aboard JWST allows us to see beyond the dust and gas, providing a clearer picture of the mass distribution in these early galaxies, which was much less than earlier inferred from less advanced telescopes. This shift in understanding also impacts the simulation models used by astronomers. These models will now be recalibrated to account for smaller, yet more plentiful, early galaxies. This recalibration could help us better predict and understand not only the formation of galaxies, but also the types of stars they host and the potential for planets around those stars, which has implications for finding habitable worlds in the future. Furthermore, these insights from the JWST underscore the telescope's vital role in modern astronomy. By providing a more accurate picture of the universe's early days, JWST helps refine our knowledge about dark matter, cosmic inflation, and the web of galactic filaments that structure the universe. Each revelation not only answers old questions, but also poses new ones, keeping the cosmic mystery as enticing as ever. The JWST's ability to observe in the infrared is crucial because this light can travel through cosmic dust that often obscures other wavelengths. By using infrared, JWST can see the unseeable, the actual forms of galaxies shrouded in the early universe's dust clouds, providing us with clearer, more accurate pictures of what the universe looked like billions of years ago. H galaxy JWST observes is a time capsule containing stars as old as the galaxy itself. By analyzing the light from these stars, astronomers can determine not only the age of these galaxies, but also their chemical composition. This data helps scientists understand how quickly elements necessary for life, like carbon and oxygen, formed after the Big Bang. Early galaxies often interacted and merged, a process that is less common in the current, expanded universe. JWST's observations suggest these interactions were crucial in the growth and development of galaxies, leading to diverse galactic shapes and sizes that challenge previous assumptions about galactic evolution. Dark matter, an invisible substance that does not emit light or energy, is thought to make up a substantial part of the universe's total mass. JWST JWST's findings indicate that dark matter played a significant role in the formation of early galaxies, influencing their shape and speed of formation. Cosmic inflation refers to the theory that the universe expanded exponentially within fractions of a second after the Big Bang. The structure and distribution of early galaxies, as seen by JWST, provide indirect clues about this rapid expansion and help validate some of the key models used in cosmology. Galaxy clusters are the largest known gravitationally bound structures in the universe. By observing the nascent stages of these massive entities, JWST helps astronomers piece together the evolutionary timeline from individual galaxies to massive galaxy clusters. The space between galaxies, known as the intergalactic medium, carries traces of elements expelled from galaxies. JWST's sensitivity allows for detailed measurements of these elements, providing insights into the processes that fuel and halt star formation in galaxies. Supernovae can influence the formation of galaxies by dispersing elements heavier than helium into space, which can then become part of new stars and planets. Observations by JWST reveal how these explosive events shape the chemical complexity and physical growth of early galaxies. The earliest black holes are believed to have formed from the remnants of massive stars or through direct collapse of massive gas clouds. JWST's data is critical in understanding these origins, revealing whether early black holes were as common as stars in some galaxies. The temperature within a galaxy affects everything from star formation to the movement of gas. JWST's instruments can detect temperature variations across galaxies, helping astronomers determine how active these galaxies were in forming new stars. Star formation rates can tell us a lot about the health and lifespan of a galaxy. JWST's detailed observations show that early galaxies had periods of intense star formation followed by lulls, suggesting a pulsating rhythm rather than a steady flow of star creation. Galactic winds, streams of charged particles expelled by stars, can affect the formation of stars and the distribution of elements across a galaxy. The JWST has captured some of the best images of these winds, illustrating their role in sculpting galaxy structures. By comparing the properties of ancient galaxies with those closer to us in time and space, astronomers can track changes and growth over billions of years. This comparative analysis is crucial for understanding the life cycle of galaxies across the cosmos. Cosmic dust plays a critical role in blocking and absorbing light, which affects what we can observe. JWST helps trace the life cycle of dust from its origins in supernovae and dying stars to its role in forming planets and new stars. The findings from JWST are paving the way for future missions aimed at exploring specific elements of galaxy formation and evolution. Each new discovery feeds into a larger picture, continually refining our cosmic models and inspiring the next generation of space telescopes. One of the less discussed, yet vital, aspects of missions like JWST is how they engage the public's imagination and interest in space and science. Since these missions not only expand our knowledge, but also inspire future scientists and deepen the public's connection to the universe. As we continue to receive data from JWST, its legacy is already being cemented as a transformative tool in the field of astronomy. Its revelations are crucial in our ongoing quest to understand the origins, structure, and fate of everything from tiny stars to massive galaxies and beyond. Understanding the size, structure, and nature of early galaxies leads to profound philosophical questions about our place in the universe and the processes that govern it. The more we learn, the more we realize how much remains unknown, challenging our perceptions and expanding our curiosity. JWST has not only looked at galaxies, but also examined the cosmic microwave background radiation. This relic radiation provides clues about the universe's earliest moments. Studying these faint signals helps astronomers piece together the complex puzzle of cosmic evolution, offering a direct link between the universe's infancy and the large-scale structures we observe today. Emerging data suggests that magnetic fields played a role in shaping the structure and dynamics of early galaxies. JWEST's capability to indirectly observe these magnetic fields through their effects on cosmic dust and ionized gas opens new avenues for understanding how galaxies evolved their spiral and elliptical shapes. By analyzing the light spectra from distant galaxies, JWST has revealed a surprising chemical richness in these early cosmic structures, finding complex molecules and dust that were instrumental in star formation. These findings suggest that the building blocks for life as we know it may have been common, even in the universe's youth. JWEST's observations have also focused on understanding how supermassive black holes grew to their enormous sizes. By observing the quasars powered by these black holes in the early universe, astronomers are piecing together the rate at which they must have accreted mass to reach their massive sizes so quickly after the Big Bang. Gravitational lensing, where the gravity of a foreground galaxy bends the light from a background galaxy, has been observed in unprecedented detail with JWST. This phenomenon not only magnifies distant galaxies, but also gives insights into the distribution of dark matter in lensing galaxies, helping astronomers refine models of galaxy formation and evolution. Proto-galaxies are the predecessors of fully formed galaxies, and JWST has provided a glimpse into their star formation cycles. These cycles shed light on the conditions necessary for galaxy maturity and the transition from chaotic early structures to more stable, star-filled galaxies. JWST has revealed how the cosmic environment influences galaxy formation. Factors like radiation pressure, cosmic shocks, and intergalactic winds all play a role in how galaxies form and evolve. Understanding these factors helps astronomers predict the types of galaxies that might arise in different parts of the universe. Galaxies are not isolated entities. They exchange material with their surroundings and other galaxies. JWST has observed these processes, often referred to as intergalactic pollination, where elements and dust are transferred between galaxies, aiding in the cosmic cycle of matter. The data from JWST is paving the way for future missions that might focus even more closely on specific aspects of galaxy formation. The upcoming missions are expected to build on JWST's findings, perhaps focusing on cosmic phenomena such as black hole growth or the detailed structure of the cosmic web. Beyond its scientific achievements, JWST's findings have significant implications for education and public outreach. They provide fresh material for textbooks, documentaries, and science curricula, inspiring a new generation of astronomers and fostering a broader public appreciation for science. One of JWST's roles is to measure the extragalactic background light, EBL, which consists of radiation accumulated over the entire history of the universe. This background light is like a cosmic echo of all the stars and galaxies that have ever existed. Studying the EBL helps astronomers determine the formation rate of stars over the cosmos's history and provides insight into the periods of peak star formation. Through JWST, we are beginning to understand not just how galaxies form, but how they die. Observations of galaxy, mergers, and the dying throes of once active galaxies provide us with a clearer picture of the life cycle of these massive cosmic structures. This life cycle plays a crucial role in the cosmic web that structures the universe. The JWST's advanced infrared capabilities allow us to see wavelengths of light that were previously inaccessible. This breakthrough provides unprecedented views of celestial objects hidden behind cosmic dust, unveiling new stars, planets, and possibly even the elusive signals from the first moments of the universe's existence. JWST's findings also have implications for the search for life beyond Earth. By understanding the atmospheres and compositions of exoplanets in young galaxies, astronomers can better assess their potential habitability and even pinpoint environments where life might arise. JWST has shed light on the cosmic recycling processes, where old stars die and disperse their materials into space, which then form the building blocks for new stars and planets. This cycle is crucial for the chemical enrichment of galaxies and has implications for the potential complexity of life-supporting molecules throughout the universe. The technological advances and findings from JWST are setting the stage for the next generation of space telescopes. These future observatories will build on JWST's discoveries, pushing the boundaries of what we can see and understand about the universe, potentially revealing more about dark energy and the true nature of the cosmos. JWST is providing glimpses into the cosmic dark ages, the period after the Big Bang, but before the first stars ignited. Understanding this era is crucial for explaining how the universe evolved from a uniform hot soup of particles into a rich tapestry of galaxies and vast cosmic structures. The data from JWST is not just rewriting our cosmic maps, it's also challenging and refining theories in physics. By providing empirical data about the early universe, JWST helps theoretical physicists test hypotheses about cosmology, gravity, and fundamental forces in conditions impossible to replicate on Earth. The stunning images from JWST do more than advance science. They also have a profound cultural impact. These images captivate the public imagination, inspire art, and influence our metaphysical conception of space, reinforcing the intrinsic value of space exploration. As we continue to decode the mysteries of the universe with the James Webb Space Telescope, each discovery enriches our understanding of the vast cosmos. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.